Hoping you're having a nice day. My name is Julieta Ibarra Maldonado, and today I'm talking about the dielectric and viscoelastic behavior of PMMA and PVB films containing barium titanate particles. Barium titanate is one of the most important dielectric materials in the electronic industry. It's widely used in multi-layer capacitors, semiconductors, thermistors, and piezoelectric devices. This ceramic is both chemical and mechanical stable and exhibits outstanding dielectric and ferroelectric properties. PVB is an amorphous thermoplastic commonly used as a binder or adhesive in composites, but its main use is in automotive industry, bonding glass sheets in laminated windshields. Similarly, PMMA is also an amorphous thermoplastic with characteristics such as lightweight, impact resistance, biocompatibility, but is also well known for its low refractive index, which make it useful in optical applications and an excellent candidate to replace glass. In this work, barium titanate particles were added to both PMMA and PVB to study their effect on the viscoelastic and dielectric responses of the polymers. We prepare composite films with particle concentrations of 0, 10, 20, and 38%. The particles were synthesized using a combination of salt gel and solvothermal methods, following the procedure reported by literature, and we obtained spherical particles. These particles were dispersed in chloroform during 15 minutes using sonications. Then the polymers were added and the suspensions were stirred for 2 hours, resulting in a polymer solution that were deposited on a Teflon coated paper using the tape casting technique and dried in an oven at 50 degrees Celsius for 1 hour, producing films with thickness between 90 and 120 micrometers. For characterizations, we use dynamic electrical analysis, or DEA, to measure dielectric properties. Measurements were taken in isothermal steps of 10 degrees Celsius from 20 to 140 degrees Celsius, sweeping frequencies from 20 Hz up to 2 MHz. We also use dynamic mechanical analysis, or DMA, to evaluate the viscoelastic response. In this case, we perform a temperature sweep from 20 to 140 degrees Celsius at different frequencies of 0.1, 0.3, 1, 3, and 10 Hz. DEA allows to measure the complex permittivity with both real and imaginary components, and from that calculate the loss factor known as tangent delta. Similarly, DMA measures the complex elastic modulus and its loss factor, also called tangent delta. From the data collected at different frequencies and temperatures, activation energies and relaxation times were calculated for the chains and dipoles in our composite films. This gives an insight into how strongly the particles interact with the polymer matrix. The DMA results show that in PMMA the particles cause mechanical restrictions, increasing the activation energy needed for cooperative chain motion. At the same time, relaxation times decrease indicated reduced local mobility. Also, shifts in the glass transition temperatures were observed compared to pure PMMA films. For PVB, however, the addition of particles caused very little change in either activation energy or relaxation times, suggesting weak polymer particle interactions. On the other side, for DEA, or dynamic electrical analysis, show that in PMMA increasing the particle content reduces dipole cooperation but increases relaxation times. This suggests that the particle act as a change carrier, helping dipoles but slowing down their overall response. Meanwhile, in PBB, we saw the opposite trend. Activation energy increased and relaxation time decreased, indicated at some atomic level interactions between the polymer and the barium titanate particles. In summary, the effect of barium titanate strongly depends on the polymer matrix. PMMA shows clear mechanical and electrical modifications, while PBB remains almost unaffected mechanically but still exhibits changes in dielectric behavior. I hope you like my poster, and thank you very much for hearing and paying attention to this video and also to the poster. Hope you have a nice day, and thank you very much.